All right, let's take a look at our lesson today on L'Hopital's rule. So, oh goodness, limits. I know y'all missed them so much. They're back. Yay. Okay, I know you're probably like giving me, like, Dr. Wright, stop. Okay, so this is just a reminder from way back in the day when we did limits, which has been some time ago. Let's just remind you what we were doing algebraically. What did we do? So our first step was to substitute the x value in. That's what we did. And we hoped that if we got a number, we were done and check. Remember, if we got 0 over 0 or infinity over infinity, we kept going. We kept going and we tried different stuff. We tried to factor. We tried multiplying by the conjugate. We tried fixing complex fractions or trig properties. Remember, that's what we did algebraically. If we got a number over 0, if you recall, then that meant that there was a vertical asymptote, and we needed to figure out whether it was, like infinity. We're going both, oops, wrong way. We were going both to infinity or, some combo, either one of these. So that was our work with limits previously. Does that ring a bell? Remember that? Okay. So what we're going to do now is we actually have another way to do type 2 limits. We have another way to do these limits, type 2. And the other way is called, and it only works on this kind, 0 over 0 or infinity over infinity. That's all it works on, okay? And the way that we're doing that is a rule called L'Hopital. Now, how many limits would he have had to have done to figure out this rule? I have no idea, but it's a very cool rule. It's very cool. It only works for type 2 limits, though. Now, if you don't want to use the rule, you could just do it algebraically. Sometimes it's impossible to do it algebraically, but sometimes you could. So just know that now we have another option. So let's look at what the rule tells us. So this is the rule for L'Hopital. And let's just go through the wording. Suppose f and g are differentiable on the open interval containing a. So that's very fancy math talk, which just means that the function's continuous at a. All right. So this, what this is saying is that if the limit of the numerator is the same thing as the limit of the denominator, which is 0, then you can use this rule. Or if the limit of the numerator is the same as the limit of the denominator, and I put this down here, you could also do it if both tend to either positive or negative infinity. So those are our criteria for being able to use this rule. Okay, it's actually a very cool rule. Now, this is not the quotient rule. I'm just going to highlight that. It is not the quotient rule. It's probably the rule that some of us made up when we were trying to take the derivative of a fraction. You take the derivative of the numerator separately from the derivative of the denominator. I mean, that's all you're doing. All right, so it's not the quotient rule. You have your original limit. It meets one of these two criteria, either 0 over 0, infinity or infinity, and then you take the derivative of the top, you take the derivative of the bottom, and then you go again. You take the limit again. All right, so I'm going to pause here for a second. That is the rule. That's me just explaining the parts of the rule. Are there any questions about the parts of the rule? So we only get to use it on type 2 limits, right? 0 over 0, infinity over infinity. And we take the derivative of the top separately from the derivative of the bottom. They're separate. In fact, we have to even write them separately. We're not allowed to write them together as a fraction. That's not okay. Okay, you with me? All right, so let's practice this. So we've got one example here. So we do what we do first. We plug the 2 in. Let's see, what do I do? 2 minus 2. Oops. So I could do that in my head. Well, that 2 minus 2 is 0. What is that? 8 times 3. Okay. 8 times 3 is what? 24 minus 6 times 4 is 24 plus 2 minus 2. Yeah, that's 0. 0 over 0. Okay. So we're not allowed to say equals 0 over 0. That is not a thing. Okay, we would lose points for that. We can't say that. We can't even say arrow 0 over 0. They're very, very picky about this. Just very picky. So what do we have to do? Here's what we have to do to use L'Hopital. We have to say the limit as x goes to 2 of x minus 2 is 0. Okay? And then we have to say, I mean, you can write them together, but you cannot make them a fraction. Do not make them a fraction. The limit as x goes to 2 of 3x cubed minus 6x squared plus x minus 2 is 0. This is required. This is required. I'm just going to write us a note. This is required in order to use this rule. You have to write that, or you can't use the rule. I mean, that's the bottom line. You have to write this or you can't use the rule, and you cannot write them as a fraction. You just have to list them. In fact, you don't even have to write them, vertically. You can write them horizontally. It doesn't matter, but they both have to be written separately. Okay, are we clear? So this would be 0 over 0, the indeterminate form 0 over 0. So this does apply. We are allowed to use L'Hopital. So what I would like to ask of you is when you're going to use L'Hopital, of course you have to write this, then if you could just write an initial like LH. I mean, I just want you to tell me what you're doing. If you don't put that, it's okay, but that just helps me follow your work. So you're doing L'Hopital. All right, so we do the limit as x goes to 2. So the derivative of the numerator, the derivative of x is 1. The derivative of negative 2 is 0. Over the derivative of the denominator. The derivative of 3x cubed is what? 9x squared minus, let's see, the derivative of 6x squared would be what? 12x. And the derivative of x is 1. So now we try again. We try to sub in again. And this gives me 1 over 2 times, 9 times 2 squared minus 12 times 2 plus 1. Okay, so arithmetic, yay. So what is that? 2 times 2 is 4. 9 times 4, what is that? 36 minus 12 times 2 is 24 plus 1. Okay, help me with my arithmetic. What is that? That's what, 12 plus, is that 13? Is that right? Is that arithmetic correct? Yes, it's 13. Okay, so instead of my answer being, 0 over 0, it's actually 1 over 13. Now, could we have done this algebraically? Well, we could have if we knew how to factor this. It looks like it would factor by grouping. So we probably could have done this algebraically, or we could have done it, use L'Hopital. So why do it algebraically when you can use L'Hopital? Okay? So how are we with L'Hopital? Does this make sense?
It's 11.
Oh, thank you. Thank you. My arithmetic is horrible. Thank you for fixing that. Y'all like, sure, yeah, it's 13. No. Right? Is it? I don't know. Where's my calculator? 36 minus 24. What is that? 12 plus 1. Oh, yeah, it's 13, right? Is it 13 or am I going crazy? It is 13. Okay, all right. Well, with arithmetic, who knows? Who knows, right? Okay, so are we good here? Okay. Okay, so we're good, right? Okay. All right, so here we go. So let's see, if I plug a 0 in, we know our unit circle, right? What is cosine of 0? 1. Cosine of 0 is 1, and 1 minus 1 is 0, and 0 squared is 0. So here we go. We have another indeterminate form. This is a type 2 limit. So in order to do L'Hopital, we have to write our limits out. So the limit as x goes to 0 of 1 minus cosine x. Well, that's 0, right? Because cosine of 0 is 1. And the limit as x goes to 0 of x squared, I sub in a 0 and I get, 0. Again, this is required. You have to write this. That allows me to use L'Hopital. Okay, so let's do this. So we've got L'Hopital. Again, it would be nice if you wrote LH for me. So the limit as x goes to 0 of, okay, so the derivative of 1 is 0. The derivative of negative cosine, if the derivative of negative cosine is what? That's a positive sign, right? Because the derivative of cosine is negative sign. And the derivative of x squared is 2x. Okay, so I could actually, I'm just saying, if you see the special limit, do you see the special limit buried there? If you see the special limit, you could use it if you want, and you can ditch L'Hopital. I'm going to do L'Hopital one more time. Okay, and I can also, we can look at the special limit, but I'm going to do L'Hopital one more time because sine of 0 is 0 and 2 times 0 is 0. So, of course, but we'd have to write this again. The limit as x goes to 0 of sine x is 0. And the limit as x goes to 0 of 2x is 0. Again, required. So yes, we can use L'Hopital. I'll write LH again. So the limit as x goes to 0. So let's see, the derivative of sine is cosine. And the derivative of 2x is 2. So cosine of 0 is 1, and I get 1/2. Which is the exact same thing I would have gotten using the special limit, right? So just as an aside, just for fun, and y'all are like, no, that's not that much fun. Okay, it's fun to me, just for fun. So using the special limit, I would pull the, let's see, there's the 1/2 times sine x over x. And we know the limit as x goes to 0, sine x over x is 1. So we know this is 1/2 times 1, which is 1/2. So you would get the same answer either way you chose to do it. You know, either way is the same answer. It's just a choice.
So you can use
L'Hopital
rule on when you already use it on?
Yes. Yes. As long as, that's a good question, as long as the rewrite, which is this one right here, as long as the rewrite also gives you 0 over 0 when you try to take the limit again. You can use it multiple times. Yes. The final answer is 1/2. Yes. Whether you choose to do L'Hopital twice or whether you choose to break off L'Hopital and do the special limit, you still get 1/2. Okay, does that make sense? Okay. So let's look at this one. Oh, we're going to infinity. That sounds fun. Y'all are like, no, it doesn't. Okay, so if I put infinity in there, I would get infinity in the numerator, and 2 to infinity, isn't that just really big? Oh, excuse me, e to the infinity, e to a really big number, isn't that a really big number? Okay, so this is infinity over infinity, also eligible for L'Hopital. Okay, so let's write that out. So the limit as x goes to infinity of 2x squared also tends to infinity. But don't put equals, put an arrow, because we can't equal a concept, so arrow. So the limit as x goes to infinity of e to the 2x also tends to infinity. And again, this part is required to use L'Hopital. Okay, so let's put our LH out here. It does not. You can put it in any order you want, and you can even list it as next to each other. You don't have to list them like I am vertically. So limit as x goes to infinity. Okay, so the derivative of 2x squared is what, 4x? And the derivative of e to the 2x is a chain. It's 2e to the 2x. Okay. Looks like I'm going to get infinity over infinity again, right? That's what it looks like. So let's do L'Hopital again. Of course, I need to do my setup. So the limit as x goes to infinity of 4x also goes to infinity. And this one we'll just put next to each other. The limit as x goes to infinity of 2e to the 2x, that also goes to infinity. Okay, so again, this part is required. Now we can use L'Hopital one more time. The limit as x goes to infinity of, okay, the derivative of 4x is 4, and the derivative of 2e to the 2x, let's see, so that would be another chain, so it'd be 4e to the 2x. Okay. So the derivative of the numerator is 4. That's not going to be a 0 anymore, so I can't use L'Hopital. What happens to the bottom? The bottom grows without bound, right? Do we remember that special limit? I'm just going to remind you. The limit as x goes to infinity of 1 over x. Remember that? What does that special limit go to? Remember that? No? 0. It goes to 0, right? Because the bottom grows without bound. So the whole fraction gets smaller and smaller and smaller. This is the exact same, this is the same concept as this, that the denominator or bottom is going to get bigger and bigger and bigger and bigger, and the numerator stays stationary. So this is going to also go to 0. Okay, that goes to 0. There we go. All right, so we have one more problem to do. Let's look at this one. Okay, so yay, a free response problem. That looks very exciting. I know. Okay, so let's read through this. So we have a particle moves along the y-axis. So it's moving along the y-axis. Okay, so its position at any time is that. Okay, that's nice. That's its position. Show that the velocity of the particle at time t is given by this. Show that. So we know what that means, right? We've encountered that before. That means basically prove or demonstrate. So we've got to do the math, right? Demonstrate, do the calculus. Do the calculus. That's what it wants us to do. It basically wants us to go from, this to this. Okay, well, we can do that. So we look at this thing right here. Okay, what kind of rule are we going to use to take the derivative of that? What's our overall template for that? It's going to be product rule. Product rule. With me? It's product rule. So according to our product rule, so FG plus FG, first things first, second things second. This I'm going to make as F and this part as G, right? T squared is F and tangent of 1 over T is G. That looks fun. All right, so V of T equals. So we take the derivative of F, the first one, the derivative of T squared is 2T. We copy and paste the second function, plus. We take we copy and paste the first function, T squared, and we take the derivative of the second function. Now, the derivative of tangent of 1 over T is going to be a chain, right? And so I'm just going to remind us. So this part in here, 1 over T is the inside function. 1 over T is the inside function. So we take the derivative of the outside. So the derivative of tangent is secant squared. Copy and paste the inside. Now we multiply by the derivative of 1 over T. So I'm going to go out here to the side. Just going to remind you, 1 over T, we could also write as T to the negative 1, which is actually would be easier to do the derivative if we thought of it that way. All right, so the derivative of the inside, the derivative of T to the negative 1 would be negative 1T to the negative 2. Right, are we okay? So that's the run through with the calculus. The next step is just prettying it up with algebra. That's all the calculus. So let's rewrite. Actually, the first part is pretty good. 2T tangent of 1 over T. That looks pretty good. The second part is a bit of a mess. So you've got T squared. This part right here, I'm going to rewrite and pull up to the front because it's just a variable. So it would be like negative 1 over T squared, right? That's what that in blue would be. And then secant squared of 1 over T. Okay, we're still just doing, now we're doing algebra. Okay, so T squared times 1 over T squared, that's just going to give me a 1, right? Actually, technically a negative 1. So v of t is 2t tangent of 1 over t minus secant squared of 1 over t. And we're verifying those two are the same. Okay, so check. We have done part A. We showed, we demonstrated, we did the calculus that when I take the derivative of that y of t function, I do get what they said.
Wait, how did you get rid of the piece?
Oh, t squared times 1 over t squared is 1.
Yeah.
Yeah. Okay. Are we okay? That's part A. So they're just saying, oh, prove that. Okay, we did. Let's see part B. At time t equals 4 over pi, is the particle moving toward the origin or away from the origin? Toward the origin or away from the origin? Let's highlight that. Are we going toward the origin or away? So let's look at what's happening. It says that the particle is moving along the y-axis. So it's basically going like this, right? It's going up and down along the y-axis. So how am I going to tell? Let's think back to particle motion. If we're going down, and if we're going up, going down would be when the derivative is negative, right? Down is when the derivative is negative, up is when the derivative is positive. So this would be derivative negative, derivative positive. We're just trying to think through what we're doing. So I obviously need to find values from the derivative. Okay, well, we can do that. So we need to find v of 4 over pi is going to be 2 times 4 over pi tangent of 1 over 4 over pi minus secant squared of 1 over 4 over pi. Oh, we love complex fractions, don't we? Oh my goodness, they drive us crazy. I'm going to go out here to the side. 1 over 4 over pi. We're going to keep, change, flip, right? We keep the top, change division to multiplication, flip the bottom. So 1 over 4 over pi is actually pi over 4. Are we comfortable with that? Okay, that's what that is. So let's keep working through this. So this is going to be, what, 8 over pi times tangent of pi over 4 minus secant squared of pi over 4. Unit circle. Oh, that's exciting. Okay. All right, so let's see. Unit circle. Let's see. Tangent of pi over 4. Tangent of pi over 4 is just 1. Recall, we're good with that? It's just 1. So this is 8 over pi times 1 minus, let's see, secant is the reciprocal of what? Secant is the reciprocal of cosine. What is cosine at pi over 4? Root 2 over 2. So secant is 2 over root 2, and that's going to be squared. And of course, I'm not really sure what the number is. We just have to keep working it. So I've got, let's just go up here. So we've got 8 over pi minus, let's see, 2 squared is 4, and square root of 2 times square root of 2 is 2. So I basically have 8 over like 3 point something minus 2. Okay, so if I just said it was 8/3, because we're estimating here. 8/3, what is that? 8 divided by, that's what, 2? That's 2 2/3, right? Isn't that right? 8/3 is like 2 2/3 minus 2. So this is going to be it's going to be greater than 0. Whatever the number is, it's going to be bigger than 0, right? You with me? We're just approximating. So if that number is bigger than 0, then our particle is moving up, right? So it's moving away. Okay, so we would say since v of 4 over pi is greater than 0, the particle is moving away from the origin. Okay, so, all right, so we good? And we haven't even used L'Hopital yet. Isn't that crazy? Well, I bet we're going to get it in the last part. Everybody go with part B? Yes? Okay, so let's move to part C. It's the last part. The velocity of the particle at time t can be written as, okay, sure. For t is greater than 1, find the limit as t goes to infinity. Okay, we can do that. So the limit as t goes to infinity of 2 tangent of 1 over t over 1 over t minus secant squared of 1 over t. Okay, let's think about that for a second. So basically what I have is, if I put in, so let's think about 1 over a really big number. Okay, I'm going to draw a graph of tangent. I hope y'all are okay. This is just tangent. I just need to get a picture of what's happening with tangent. This is tangent. It looks like that. So as this bottom number becomes bigger and bigger, the fraction tends to 0. What is tangent of 0? It's 0. Okay, so I'm going to get a 0 in the numerator. As this 1 over t, as this gets larger and larger, what is 1 over t going to tend to? 0. It's going to be 0 over 0. So this is 0 over 0. Let's see what this would be. Secant squared, or secant is reciprocal of cosine. So what is this? So cosine of 1 over, so 1 over a really, really big number is 0. But secant of 0 doesn't even exist, right? Because secant, here's cosine. I mean, secant is right here. So, oh yeah, secant of 0 would be 1. Okay, so this one's okay. Are you with me, or are you like, what are you talking about? You're crazy. Okay, yes, okay, we don't know what we're talking about. Okay, so when I don't know what's going on, I draw the graphs of the trig functions. That helps me. That just does. And I don't know even what's going on here. That's crazy, right? So I drew tangent. And are you okay, first of all, are you okay that this is 0 over 0? Are we okay with that part of it? Or you're like, no. So tangent of 0 is 0, and 2 times 0 is 0, and as t goes to infinity of 1 over t, it's 0. So that's 0 over 0. Are we okay with that part? That part's going to need L'Hopital or something. This next part right here is, so secant squared. Let's just look at secant. Just secant by itself. This is the graph of secant. Secant is the reciprocal of cosine. Cosine starts at 1 and goes down. This is the shadow graph. So secant is on top of it, right? That's how secant's graph looks. Because again, I don't even know what's going on unless I draw the graph. So when this t gets bigger and bigger, this fraction tends to 0. So secant of 0 is 1, right? Secant of 0 is 1. So this is okay. It's just going to be 1. I don't need to worry about that part. So I could actually split this limit up. The limit as t goes to infinity of 2 tangent of 1 over t over 1 over t minus the limit as t goes to infinity of secant squared of 1 over t. That's what I should really do, because this part is just going to be 1 squared. That one's kind of done. It's the first part that's going to be more challenging. Are we okay with that? Okay. So, L'Hopital on that first part is still going to be painful. I hate to tell you. Oh no, I think we have a thing going. Okay, so we're going to, that part we're done. This part, I'm going to highlight it. We're going to look at it further. We're going to keep going with this part. Okay, we're going to keep going. We already know that's 1. Okay, so we're going to do L'Hopital. So the limit as t goes to infinity of 2 tangent of 1 over t. That goes to 0. The limit as t goes to infinity of 1 over t. That is 0. And if you recall, to use L'Hopital, you'll have to write this part. Okay? So that part is required. All right, so I'm going to keep going down. So I'm going to do L'Hopital. So the limit as t goes to infinity. Okay, so the derivative of 2 tangent is 2, let's see, the derivative of tangent is secant squared. Copy paste the inside. The derivative of, and we actually already did the derivative of t to the negative 1, didn't we? Remember that? That's negative 1 over t squared. Okay, that's multiplied. We're chaining it. Over the derivative of 1 over t is, negative 1 over t squared. Excuse me, t to the negative 1, not negative t. Look what beautiful thing happens. Okay, that cancels with that. And so we actually already found what the limit as t goes to infinity of this secant squared to the 1 over t is, didn't we? We found it up here. Isn't that 1? So, sorry for the crazy work everywhere. So this is going to be 2 times 1 minus 1 squared. That's what our limit is. 2 times 1, so that's what? 1. All of that for an answer of 1. That's pretty exciting.